Alright, hello class. Today we're going to be talking about one-dimensional motion in general, and we're going to be doing, displacement, velocity, acceleration, problems that deal with that kind of stuff. I'm going to be pulling example problems from the book, and maybe one or two problems out of the back of the chapter for this recitation. Okay, so let's start off with a definition for displacement. We're going to talk about some change in an x-coordinate here. And this formula for displacement is going to be delta x is equal to x2 minus x1, x2 being your finishing location, and x1 being your starting location. So after that, one of the biggest questions is going to be, well, how long did it take you to get from one place to another? So that'll be our average velocity. So here what we can do is we can say, all right, well, then delta t, or the difference in time between 2 points. So this is going to be t2, which is going to be the time at which we arrive at this second position, minus t1, which is going to be the time at our starting position here. And so then what we can do is a little bit later is we can say that our average velocity, or v bar, as I always saw it in my classes, is that delta x over delta t. This is equal to x2 minus x1 all over t2 minus t1. Now, so if we were to involve a little bit of calculus with this, what we could end up doing is we could take the limit as delta t approaches 0 of delta x over delta t, and this is going to give us your instantaneous velocity. So this is going to be your velocity at any point in time. And we can also just say that this then is going to be equal to dxdt, or the time derivative of our displacement or position function. Either word is very, very usable in either sense. Units, let's keep track of them. We usually use meters for displacement. We'll use seconds for time, and then meters per second for velocity. Okay, so as you guys can see on the board here, I've set up a problem with a dragster here. And so in this problem, we want to find what the dragster's average velocity would be over this interval here. So we want to find what v bar is in this case. So we have our finishing position, our starting position, our ending time, and our starting time. So what we can do is we'll take our formula for v, and all we have to do here is plug and chug. But I want you guys to see what it would look like numerically. So we have 100 meters minus 10 meters, and we're going to put this all over 15 seconds minus 2 seconds. And so then with some quick maths here, we can do the subtraction on the top and get 90 meters over 13 meters, or 13 seconds on the bottom. And so then from there, all we have to do is plug this into our calculator, and we will get 6.92. meters per second. So that's just a really quick example on how to use that average velocity function. Okay, so now what I've done is I have erased the 2 times at the top. We're not going to be considering those at the moment, but what we're going to do is I've now defined the dragster's position as a function of time. So what we're going to do is we're going to find the instantaneous velocity function, and then we're going to plug it in. We're going to plug in 100 meters into our function here, and then we're going to find how much time it takes for this dragster to, or we're going to find the velocity that it has, the instantaneous velocity at time, or the second time. Okay, so in order to do that, we're going to take the derivative here, and so on this side we're just going to have v of t. Our 10 meters is going to go away because the derivative of a constant is just equal to 0, and then we're going to take the derivative of this guy here, and so then the 2 is going to come down and multiply by this other coefficient, and then we're going to subtract 1 from the exponent. So now we're going to have that this is going to be equal to 15 meters per second squared over t. And so now we've found the instantaneous velocity function, and it seems to be 15 meters per second times t. And so then next up, what we have to do is we can also do is in order to, so we've taken the derivative, we found the velocity function. So now what we're going to do is we're going to plug 100 meters in here, and then we're going to solve this equation for t. And so then when we find that t, we'll plug it in here in order to find the instantaneous velocity at the second time here. So what we're going to do, we'll plug in our 100 meters, subtract 10 from the other side, and then we're going to divide both sides by 7.5. And then we have to take the square root of both sides to get t all alone on this side. So to recap, subtracted 10 meters from both sides, or first of all, plugged in 100 meters on this side for x. Subtracted 10. Divided both sides by 7.5. Took the square root to get t alone. So then we can do this pretty quickly here, and we'll get 90 over 7.5, and then we'll take the square root of that. And so now this would be a good point to check our units just to make sure we haven't done anything wrong. So on the top we're going to have meters, and on the bottom we're going to have we're going to have meters per second. But what's going to happen is this meters here is going to cancel with this meters here, right? So I'll plug in the units here, so that'll cancel with that. Now we have 1 over second squared on the bottom here, and so then we can re-invert that and bring the second squared up to the top. And then since this is just multiplied by it, what we can do is we can say, all right, well, we can take the square root of second squared, which is just going to give us seconds. So then we know that this quantity here is correct because time is measured in seconds. Okay, so let's take the square root of 90 over 7.5. So 7.5 is 12, so then the square root of 12 is just going to be 2 square root of 3 seconds. Let me write that clearer. It's 3, and so then that's going to equal 3.46 seconds. So then we can plug this number into our velocity function here, and then we will get our instantaneous velocity at 100 meters. So then let's write that out. And let me chop off everything, all the other numbers. Okay, so we're going to get 15.9 here, or 51.9, sorry, said it backwards. And so this should be meters per second, because this second cancels with the square there, and you're just left with meters per second. Okay, so the process for finding average acceleration is quite similar to the process for finding average velocity. So you have a bar, which is equal to v2 minus v1 all over t2 minus t1. It's the same thing, which can be also rewritten as delta v over delta t, which now, if you take the limit as delta t goes to 0, we can see that of delta v delta t, we can see that this is now just dv dt, which dv dt, oh, this is for finding instantaneous acceleration, by the way. So then we have dv dt here, right? And so then we can plug in what v is. Now remember, v is just dx dt. And so then we can have this derivative on the outside. And we can have dx dt on the inside here. And then we can also pull out this this second function here, or the second derivative here, and we can have d squared of x, which is just the second derivative of the position function. Okay, so now with our first equation for acceleration here, we're going to assume a constant acceleration, and so we can say that a bar is just equal to a in this case, because the acceleration is going to be the same no matter what the time is. And we're going to say that t1 is our initial time, and we're going to take that as our time is equal to 0 seconds. So which allows us to do this, and just cancel that out. And so then I'm going to start replacing our 1s and 2s with i's and f's for final and initial. And so now what we can do is we'll multiply t to the other side. So then we'll have at is, and this is it's just tf is equal to vf minus vi. And so then we can get our first kinematic equation, where vf is equal to at plus vi. So this is saying that our final velocity is equal to our acceleration times time times or plus our initial velocity. Okay, so next up, another thing that we know about our average velocity is we know our other formula for it. And now, one thing I'm going to do is, since t1 is equal to 0, we're just going to get rid of it. And then T2 is just the time it takes to traverse this distance here. So after that, what we want to do is we're going to set our two formulas equal to each other. And then we're going to plug in our equation that we derived here and then solve for xf. So first thing we're going to do is we are going to plug that in. So vi over 2 plus 1/2 at plus vi over 2. So from here we can combine our vi's. So I'm just going to get rid of this one and then take away the 2 because we're combining them. And then we're going to multiply t to the other side and then add xi to both sides. So then we get that xf is equal to vit plus 1/2 at squared plus xi. And now this is more commonly found in this form, like this. xf is equal to 1/2 at squared plus vit plus xi. So you have your quadratic term here, you have your linear term here, and this is your initial condition here. And this is going to be for constant acceleration only, just so we have that. Okay, so next up we can take our two relationships that we've derived here and we can find another one that will be helpful when you're only using certain quantities. So what we're going to do is we're first going to just solve this equation here for t. So to do that, we're going to subtract vi to the other side. So we're going to have vf minus vi all over a, because we're going to then divide a to the other side, and we're just going to have t left over. So then next we're going to plug t into this equation here, and then we're going to solve this for vf. And then we're going to have another useful relationship. Okay, so let's do that. So then we have xf is equal to 1/2 a vf minus vi over a squared plus vi times vf minus vi over a plus xi. So first thing that I think we should do is let's FOIL this. So this is going to give us 1/2 a. So we're going to have an a squared on the bottom. So this is going to be 1 over 2a. And then we can now just FOIL this because we don't have anything left inside the parentheses on the bottom because we can just take that out. So then we'll have vf squared, and then we'll have minus vf vi, but we're also going to have a second one, so we can make this a 2 vf vi, and then we're going to have plus vi squared. Let's distribute the same thing over here. So now we're going to have 1 over a here, and then we're going to have vi vf, and then this is going to be minus vi squared. Okay, and then we have our plus xi at the end. From here we can do a couple things. So just remember that all this is multiplied by 1 over 2a. And so one of the things I want to do is I want to take this xi and get it to the other side first. xf minus xi. And then I'm going to multiply both sides by a. So now we just have a 1/2 of this quantity times, or plus this quantity. Should probably add a plus sign in there. So what we can do is we can say that this is v1/2 squared over 1/2. This is minus vf vi plus vi squared over 2 plus vi, oh, that should be a v, a vf minus vi squared. And we've gotten rid of that xi that's over here now. So now we can collect some like terms here. So these are going to cancel right off the bat. And then you can combine these two terms. So this is going to give you a negative, it's going to give you a negative vi squared over 2. So then what we can do is we can say, all right, well, how about this? Let's combine those. So I'm going to keep writing what we have on the left side here. We're going to keep that the same. And then we're going to have vf over 2. Combine those. We have minus vi squared over 2. Now I'm going to multiply both sides by 2. So then we're going to have 2 xf minus xi times a. And then we can solve this equation easily for vf now. So then we get that vf squared is going to be equal to vi squared plus 2a xf, or we can even make this simpler. So from our displacement lesson, we know that this is going to be the difference, or the difference between these two, so we can just write this as delta x, just to keep it simple. And we've derived another equation here. Another relationship that we kind of skimmed over before is one that we'll derive now. So we kind of already went through this, but so if we have v bar is equal to vf plus vi over 2, and v bar is equal to xf minus xi all over tf minus ti, and we set them equal to each other like we did before, we'll get vf plus vi over 2 is equal to xf minus xi. And if we assume that ti is equal to 0, we can just get rid of all of this and write over t. And then if we take this equation and we multiply both sides by t, we get vf plus vi over 2 times t is equal to xf minus xi. And then, like we said before, we can make this equal to delta x. And then this side will just stay the same. So we'll have vf plus vi t, oh, not t, but you get the picture. And we can derive another useful relationship. Okay, so the next concept that we should be exploring is definitely free fall. So in free fall, on or near Earth's surface, we have that the value of g is equal to 9.81 meters per second squared. Some classes will have you using 9.8. 9.81 is just a tad more precise. We will not be using 10 for g in this class for sure. But otherwise, now let's take a problem in free fall. So say we have a building here, right? And so this is the ground, and we're going to drop a ball off the top of the building. We're not going to throw it, we're just going to drop it. So we can use one of our kinematic equations here to find out how fast this ball is going at any point in time. We can find out its position at any point in time. But for our purposes here, we're just going to use, we're just going to try to find its velocity at the bottom here. So we want to know, first of all, well, how long does it take for this ball to hit the ground? That's going to be our first problem. So we're going to try to find t. Now, there are probably a couple other ways to do this, but for our purposes here, we're going to use our xf is equal to 1/2 at squared plus vit plus xi. So right off the bat, we can say that if we're just dropping this ball, we're not giving it an initial velocity. So this term here goes to 0. Next up, we can say, all right, well, xi is just going to be the height of the building. So whatever this height is, this is going to be equal to xi. And our final position when the ball hits the ground is going to be xf, which is going to be equal to 0. Okay, so now since this ball is falling, and it's going to be moving downwards or towards the ground, we're going to say that g is equal to negative 9.81 meters per second squared. And so this is our acceleration due to gravity. So we can say that negative xi, or how about we keep xi positive? So xi is going to be equal to negative 1/2 at squared. Remember, this is equal to 0 because that's at ground level. At squared. And so now, if we solve this equation for t, we're going to have t squared over here, and then we're going to have negative 2xi over a, so we have to divide by a. And then we'll take the square root of both sides, we'll get t. So we'll get the square root of negative xi over a. Now you're probably wondering how we're going to get away with having a negative inside the square root. Well, we already have a negative inside there because a in this case is going to be equal to g. So then we can just go ahead and do this, and we can say that t is now equal to 2xi, the absolute value of a. So, and then xi is going to be equal to h. So we have 2h over the absolute value of a, or the absolute value of g, for plugging in all our constants. So now let's give ourselves a height. Let's say this is, I don't know, 50 meters? Yeah, 50 meters. H is equal to 50 meters here. So then we can plug that in, and we can say that t is equal to 2 times 50 all over 9.81. This is obviously still in the square root. And so we have 100 over 9.81. Do that on our calculator real quick. Should come out to a little bit over 10. And then we take the square root of that. Okay, and so when we plug this all into our calculator, we end up getting 3.19. So first thing we should do is really check our units here. So now we have inside the square root here, we have 2, which is just a coefficient, so no units there. H has units of meters, and then G has units of meters per second squared. And so if we were to do our analysis here, we would have the square root of meters over meters per second squared. These would cancel. Then we have the square root of seconds squared, which is just equal to seconds. So we have now found our units here, and they've come out right. We get time. Okay, so for this next example, what we're going to do is we have our ball down at this position here, xi. It's on the ground. It's at ground level. And we're going to give it, we're going to throw it up in the air and give it some initial velocity vi to where it travels to its peak position at xf. So now for this example, what we're going to do is we're going to go through the steps that we can take to find the peak position and the peak time, so the time it takes to get to the peak and where the peak exactly is. So first off, we have to note again that A is just equal to G here. And here we can take our kinematic equation and we can immediately say that the velocity, the final velocity squared is going to be equal to 0, because at its peak, it's going to stop for a second. And it's just going to, for just an instant, its VF here is going to be equal to 0. So we can cancel out that term immediately. Next thing that I want to undo is I want to unpack delta x here. So delta x is just equal to xf minus xi, and xi is our origin point, so then we can set that equal to 0. So then we get that delta x is just equal to xf. Next up, we can finish rearranging this equation because we have a 0 on this side. So now if we move our initial velocity over here squared to the other side, we'll get that here. And then we divide this equation by 2a, and there's our 2a. And remember that we unpacked our change in position here, and that's all that's going to be left on this side. I specifically moved vi to the other side so that delta x would be positive. From there, we can just start plugging and chugging here, as that equals that. And this is a 2a here, so this is just going to be negative vi squared over 2a. And our units work out here pretty well. This negative here counteracts the negative in our g, which is negative 9.81 meters per second squared. And this points in the downward direction, and that's where we get our negative from. So just a simple calculation, we plug in our numbers. 10 squared is just going to be equal to 100. The negative from G cancels out with the negative that we get from subtracting VI squared to the other side. And then multiplying by 2a, we just get this ratio. And we find that our peak position is equal to 5.09 meters. Now, in order to find the time, we have to do something else. We're going to use the other kinematic equation that we used earlier here, where xf is equal to 1/2 at squared plus vit plus xi. So now what we can do is, or what I immediately want to do is I want to compact xf and xi together to give us a delta x. But the thing is that this is going to be negative, because if we move this to the other side, or xf to the other side, it's going to be negative, and our xi is going to be positive. So then in this case, we're going to have a negative delta x here, and that's where this negative sign comes from. Just, yeah, so this is a negative sign, and we have 0 is equal to 1/2 at squared plus VIT minus delta x. So next, in order to, since we have a 0 on this side and we have a quadratic here, we can use our quadratic equation. So 1/2 a is going to be equal to, or is going to be our a in this equation here, and vi is going to be our b, and negative delta x is going to be our c. So then next up, we can start plugging and chugging. So we have negative b here, which is going to be negative vi, plus or minus the square root of b squared minus 4ac. Our a, again, is just the 1/2 a, and then our c is going to be negative delta x. So right off the bat, remember that our a is going to be, our a here, I'm going to try to make this less blurry for you guys, but our a here is going to be negative. So we have a negative times a negative times a negative, which is going to give us a negative in the end. And so this quantity here is very similar to the quantity over here, because xf is here, this is a, which was here, there's a 2 here, and there's vi squared. So in this case, these quantities are actually going to cancel out and equal 0. They're going to give you nothing. So this entire term here in the square root is going to go to 0, and then you're just going to have negative vi over a, because the 1/2 canceled with the 2a from our quadratic formula, and so then you're just going to get negative vi over a, but a is negative because we have that up here, so that's going to be negative 9.8, and so then we just get that t is equal to 1.019 seconds. Now, you can ask yourself, does this physically make sense? And you could say yes. So think about how big g is. G is 9.81 meters per second squared. So if our velocity, our initial velocity, is only equal to 10 meters per second, then this thing is going to basically slow all the way down in just 1 second. So it would make sense that our time to reach our peak is only 1.19 seconds. Okay, one of the last things that I want to touch on in this chapter is talking about using graphs. So for our graph up here, this is a graph of our velocity function as a function of time. And so then the derivative at any point along this is the acceleration at that time period, like at that instant in time. You can do that by just taking the derivative of your given velocity function. Other than that, one other thing is to note is that the area underneath the curve of your velocity function is going to be equal to the displacement. So when you have say a velocity is say negative, so say we took another velocity graph here, and let's draw it a little bit further downwards, and you have something like this, and say these two areas are equal, then the displacement here, delta x, is going to be equal to 0. This is for v of t, because the area here and this area here are going to cancel out. So what happens is when v of t is positive, even though it might be decreasing, and this shows a negative acceleration, while this one shows a positive acceleration, this velocity here is still positive, and therefore it's still increasing in distance from the origin. But when it's down here, it's going backwards now. And even though it starts to flatten out here to where it stops, and again where it stops up here, and then this is it going back towards 0. So this is also a deceleration here. So as this increases, this is it accelerating, but in the negative direction, and this is it decelerating, but it's still in the negative accelerate or negative. It still has a negative velocity, but it's decelerating. Now, along these points here, we're going to move on to our displacement graph. And so along these points here, A, B, C, D, E, and F, we're going to talk about what the velocity is here. So you can just take the derivative here. Sorry, this marker's not working too well. But at this point, if you take the derivative here, you're going to get a positive velocity. And so this is going to be positive. At B, it flattens out. So this is going to be 0. At C, you're going to have a negative velocity. And then at D, your velocity is still going to be negative, but this is where you go back to your original starting point. Same if we added a point G here. This is also going to be at the origin. And then you go down here, and this is going to be a 0 velocity. And if you take the derivative here, this is going to be a positive velocity, and then this last point G is still positive, but you're back at the origin.